Alright, let's get started with this question. Uh, Maybe I should take a revision for binary, right?
Hey guys, Greg here. Today I wanted to talk about a common algorithm known as binary search. And there's actually two different ways we're going to deal with it. One is the traditional method, so that is basically how to search for a number in a sorted array. And there's a second sort of secret method, which I'm going to call the over-under technique, which is really common in solving LeetCode problems. Now, to implement binary search, the traditional way is given a sorted array of integers, and there can be negatives as well. And as long as that they're sorted in generally ascending order, then you can apply what's called binary search. So in the traditional way of applying binary search, you would generally do this because you're trying to look up if a certain number is in the array. So we'll say we're trying to look up if 3 is in the array. Well, we know that you could search through the array, and actually in O of n time, you could basically start at the first index or index of 0. And you could basically just keep checking all the way. So is the number -5? No, it's not. -3? No. You could keep going, and then eventually you would see 3. And this is O of n because you're basically starting at the beginning of the array and going to the end. But let's give it some more indices here. So 0, 1, 2, 3, 4, and 5. And this array has n equals 6 values. First initialize 2 pointers. So this is actually a 2 pointers technique. And people are going to get annoyed when I say pointers, but in Python and in normal languages, we generally just mean indices. So we set up an index L at the beginning, and we set up an index R at the end. So the initialization there would be setting L is equal to 0, and R is equal to n-1 would be the last index. And then basically iteratively, so in a loop here, you'd want to calculate your middle index M. Now there's actually 2 values in the middle here, because if our search space is here, well, if we go one step in, it's these two. And then if you go one step in both sides, you actually get 2 values in the middle here. And that's because we have an even number of items in our search space. And in binary search, generally what we do is if there's 2 values in the middle, you want to calculate the lower one. And that's just because we use this formula. M is equal to L plus R, so these are brackets, L plus R integer division by 2. And that integer division by 2, that basically rounds it down. That's what's going to cause it to be the lower one of the middle two. Okay, so this is your general formula there. M is equal to L plus R over 2. And so if you do it for this particular example, you get L is 0 plus R is 5. And that's going to give, of course, just 5. You integer division that by 2. That's going to equal 2.5, which rounds down after the integer division to 2. So that's the formal way to actually get that your middle index is here, although most of the time you can just eyeball it. And then you would ask the question, is the array, we'll call this array A, is the array at M equal to the value that we're looking for? So is A at M equal to, we'll call this in general the target T. Okay, so is A at M equal to our target? Well, clearly it's not because we have -2 here and we're looking for 3. Well, then after we've asked the question if they're equal to each other, well, we know it's not exactly what we're looking for, but now we're curious on if it's less than -2 or if it's bigger than -2. Because if it's less than it, then that means it's anywhere over here because we have a sorted array. And if the target is bigger than it, then that means it's anywhere over here. And so since our target is actually bigger than our current value of -2, we can basically just eliminate this entire search space here because the array is sorted. We know it's got to be in this side. At least if it was in the array, it would be in the side. This could have been a 4 and it wasn't there at all. But we can eliminate that half of the search space. And to do that, well, L and R define inclusively our search space. And so basically what you would do is set L equal to M plus 1 because we know it's not M and we also know it's not anything less than M as well. So we would do this iteratively. We move our search space over and then we calculate our M again. You could use the formula and you get that 3 plus 5 is 8. Integer division that by 2, you're going to get 4. And so this is your middle index right there. And so you would see our array at our middle index is actually equal to our target. That means it exists and we can return true in that case. Okay, but let's instead say that we were searching for 1. So if we just quickly reset here, L and R at the beginning and ends, we would get our middle index M here. The same thing would happen where we end up moving L over because our target is bigger. So we would move L over here and that would move our middle index to the same spot here. But then we would see that this does not match. So these are not equal to each other. And we see that our target of 1 is actually smaller than our current value here. So what that means is that the number is going to be somewhere in this space, which is actually just one possible value here. It means that our search space is going to be precisely over here. And so when this happens, you would just get your middle index is L is equal to R, which is equal to M. And then in this case, you would find again that your target exists and you would return true. Okay, let's change this one more time to say that we're looking for the value of -6, which ultimately does not exist in the array. So we get our middle index here. This value is not our target. And it turns out that this value is actually bigger than our target, which means you want to search in this space. And so you'd move R to be M minus 1. We cut out all of this space. And that will actually move our middle index over here because if our search space is 2 things and we're going to get to the lower of those 2, well, then we would get to that one right there. And if you were to do the math, that's just going to be 1 plus 0, which is 1 integer division by 2. That's actually just going to equal 0 because it's 1 over 2 rounded down and that rounds down to 0. And we see that this is not the value that we're looking for. And we can see our target is again less than this value. So that means that we actually want to search in this space, which doesn't really exist. But what would happen here is you'd set R equal to M minus 1, and then we get this kind of crisscross thing. The reason it was called L and R is because L was on the left and R was on the right. If we get this effect of R is now kind of to the left of L, that basically just tells us that we did not find the number we're looking for, and so ultimately we return false. Now what I'm about to say matters in some programming languages. It really just tells us that we did not find the number we're looking for, and so ultimately we return false.
Give a these examples with the target T equals -1. Okay.
Now what I'm about to say matters in some programming languages more than others. Generally the more modern ones don't care about this as much. But it turns out that this formula is actually not the most ideal one because of this L plus R thing. So you can picture this, if kind of L and R are near the end of the array like this, well then you're basically adding 2 potentially big numbers together. If you
L
did have
minus
n is equal
R.
to a million things here, then in that case you're basically doing kind of a million plus roughly a million. And there's this thing called integer overflow, which is basically if you start getting really big numbers due to like an addition or multiplication like this, well then that can cause a big problem. So generally you would want to avoid this L plus R part. And so what you could do instead is kind of a rearranging of this. You can actually get a different formula, which is M is equal to L plus, and I'm going to write this all
L
in brackets
minus
here, R
R
minus L, and then integer division by 2.
2.
So this part is the only integer division by 2 part. It's basically looking like this. It looks a little bit weird, but just to kind of prove it to you how it works here, if we have L and R at the beginning and the ends, you would get L is equal to 0. You would get R is 5, and then you would subtract 0, which is just going to be 5. You'd integer division this by 2, which is actually going to give a result of 2. And then you just add these two things together. So that again gets a result of M. Just know that if you see this formula, they're basically using it to avoid integer overflow. Okay, so again, that was number 1, which is the traditional method. It's just looking up if a value exists in a sorted array. So that's done. And now what we're going to do is number 2, which again I have called over under. So let me show you what I mean here. Let's say we had an array of true falses, and they are organized like this, where it's something like this is true, this is true, this. And I have called over under. So let me show you what I mean here. Let's say we had a
In hindsight, I think a better name is condition-based.
Array of true falses, and they are organized like this, where it's something like this is true, this is true, this is true, and then up until a point you randomly get an event like this, where this is false and everything is false, basically on some point here. So it basically divides into two pieces, where one side is true and the other side is false. And it would have worked as well if kind of this side was false and the other side was true. As long as it's basically like a divide between two different ideas, then this should work fine. So to give some real world example for this, maybe we asked if someone was sick. So someone was sick. Well, first day, yes, they were sick. Second day, they're still sick. Third day, they're sick. But the next day after that, they start testing and it's false. And basically forevermore. They might get other sicknesses, but for the certain one, it's like we were sick for a while and then now we're okay. So a question you might want to know is basically on which day did they start feeling better? So it's going to be the first of these false things right here. So what you can do is use binary search. L is equal to 0, R is equal to n minus 1, which would be 5. Calculate your midpoint, and that's going to be this one right here. And you would ask if this is false. No, it's not. It's not false. It is true. And since it is true, and we know it's kind of organized into these two pieces right here, we know that all of the stuff over here is true. And so we basically want to search in this side of the array. And so you would set L equal to m plus 1 and start the search again. And you would see that this is a false. However, we're not sure if we're looking at the first false or not. If this is really all the information we have right here, well, we don't know if this is the first false or not. It could be, but it also could not be. You actually want to set R equal to m. We know we don't want to look in this part because this one is a false, and so we don't want to be over here. However, we don't want to move prematurely past m. We don't want to go to m minus 1 because this is one of the types of things we're looking for, but it might not be the final one. So in this case, we set R equal to m, and then we start looking in this range. And so here, you would actually get your index m is this one, and you would see again that this is a false, and so you would do the same thing again. You would set R equal to m. We don't want to look over here, and this is actually when you would return in this case, is precisely when L is equal to m. This algorithm here is actually forcing us to look at the first one of these. It's a really clever idea, and I feel like a lot of people don't know you can do this for binary search. Okay, so let's think about time and space complexity here, and it's going to be exactly the same for whichever way you're doing binary search, whether it's this over under true false way, or if it's the traditional way of searching through a sorted array. It really doesn't matter. It's doing pretty much the same thing either way. Okay, so for the time complexity here, well, we know it's not going to be O of n. Otherwise, this would have just been a waste of our time. We're getting something that's faster than O of n because basically what happens here is we calculate some middle index, and then at this one step here, we are going to cut out half of the array. So right now our search space is n equals 6 many values. It could have basically been in any of these spots. So what would happen is we'd see that this is a true, and it's not what we're looking for. We're looking for a false. And so basically we know that all of the stuff from L to M here, all of this stuff is wrong. We don't want any of the search space. So we'd immediately go to L equals M plus 1. And that reduces our search space just to here. And so that in one step cut our search space down in half. Now there's only 3 different spots it could be. And that would keep happening. So you keep dividing that in 2. Although we kind of need a bigger number here. So let's say we actually had an array of 1,000 values. Okay, so I can't really draw that here, but basically you would have an index 0 with some number, say negative 100, and you go all the way up until the last index would be at 999. And we'll say this is a value of say 1,000. Okay, then basically you would get L and R are 0 and 999. You would get your middle index is about 500. And say that we were searching for a target value of 700, if that's in the array or not. Say that this saw a value of 100. Well, we kind of know that it's not anywhere in this range here. It's not going to be any of these values because 700 is bigger than this value and it's sorted. So you would move L to the M plus 1 and you'd cut out so many values here. You basically cut out all the indices from 0 to roughly 500. And so what's going to keep happening here, let's just do a little bit of quick math here. At stage 1, you'd have 1,000 different values in the search space, then you'd have 500, and then you'd have 250, then you'd have 125. You see how quickly this is going down here? This repeated dividing by 2 is exactly what you would get in a log base 2 of runtime. That's what log base 2 means. It basically means you take n and you keep dividing it by 2 every single step. And so this is very, very fast. So this has a time complexity of log base 2 of n. And the space complexity, well, that's really not too bad actually. If you just have an index L and index R, and then occasionally you get this index M, well, that's really just 3 different things that you're storing. And we don't have to do this recursively. You actually could do it recursively, although we're going to do it in loops. And so this would have a space complexity of constant. It's just O of 1 because we're just storing a constant number of variables. Now, one last thing about binary search, what's kind of cool is you don't necessarily need an array of values for this to work here. So we've kind of been assuming you have, or maybe you go and get some array that looks like this. It turns out that you can even do stuff on it when you just have like a range of values. Like say you had a starting point of 2 and you had an end point of maybe 1 million. You could actually do binary search on this as well and get to the middle index is the middle of that range, which is going to be roughly 500,000 or so. And I'm not going to spoil the fun because there's some really cool problems to solve with that, but note that that will come up as well. Okay, so let's code this up. Okay, so let's start with an array A equal to -3, -1, 0, 1, 4, and 7. So notice we have a sorted array. What you could do is kind of the, I'll call it the naive or O of n way of searching. So if you're looking up if a value is in this array, well, you could just say something like if -1 is in A. And if that was the case, then you could print true and you would see that result. And so that does get printed. And if you were to look up if 7 is in the array, it's going to look up through the entire array on how to do that. And you could do something like if 8 in the array, and that's not going to output anything because it's not. Okay, but this is a sorted array, and so to do our traditional binary search, which is basically looking up if a certain number is in the array, well, as discussed, this is going to have a time complexity of big O of log base 2 of n, or I'll just write that as log n, and the space complexity is going to be big O of 1. It's just constant space. Okay, then basically what you would do is you initialize L is equal to 0, that's the first index, and R is equal to the last index. Generally, I get this as a variable, n is equal to the length of the array A, so that you can do R is equal to n minus 1, which is the last index. And generally, you would implement this with a while loop, while L is less than or equal to R. And this is the condition because, well, in general, L is going to be less than R. But then if they get equal to each other, we're basically in this position where we're looking at the same number. Well, we actually would want this to run when they're equal to each other because that would make sure we look at that final range there. If it was just L is less than R, well, then that would basically mean when they get equal to each other, we're not going to consider that final value, and you would want to consider it. And so this loop would terminate, particularly when L is greater than R, which would basically be a circumstance like this. You would have right on the left side of L, and that just doesn't make sense. That means that we've crossed over the search space, and so that means you would return false in that case. So let's write pass for now, which just means do nothing. And so if you ever break out of this while loop here, that means we've had that crisscross, we couldn't find it, and we return false. And it's probably better to write this as a function. So we'll call this define binary search, and we'll say that it takes some array, which we'll call R. Then we'll get n is equal to the length of that array R. We get L is 0, R is n minus 1. And so while L is less than or equal to R, if we ever break out of this, we want to return false that we couldn't find it. And then in this loop here, we want to iteratively get our index M. The easiest way to write this is just L plus R integer division by 2. And this is Python, so that would totally work. But for super strict practice, you would technically want to do L plus R minus L, and then you want to integer division that by 2. And while this would work, I actually want to really explicitly say that this is the part that gets that integer division by 2, not the L over here. Okay, so we get that as our middle index, and then you would just basically ask 3 different questions. The first would be if the array at our middle index is equal to our target. So if we found some sort of a target that we're looking for, well, then you would want to return true because that means that you found what you were looking for. Now, otherwise, you are in one of 2 scenarios. The target is either bigger than your array M or your target is smaller than your array M. So otherwise, if the target is, we'll say, smaller than your array at your middle index, well, that means that your target is on the left side. To go into the left side, you'd actually need to move update R equal to M minus 1. That's what would search in the left side. And then otherwise, if this is not the case, well, then you would want to do the opposite because your target is bigger than your array M, and so you'd want to search for it in the right side. To actually search in the right side, you'd want to set L equal to M plus 1. Okay, so let's just call binary search on our array here. So binary search on the array of A, and we'll say we're searching for a target of -10. So that returns false. We'd see that we actually do have a value of 0. So if we plug in 0, that is going to be true. If we have -1, that is also going to be true. That's in there. And let's just do a couple more here to make sure. For that works as well. 7, that works as well. However, 6 is not in the array, and also 8, anything higher than that is not in the array. Okay, so that's our main traditional binary search function. Make sure that you memorize this code. Trust me, you will end up writing a lot of binary searches, so memorize how this looks and really understand it. Okay, and then there's what I call the over-under technique, but I don't want to call it that here because that's pretty loose. Basically what it is based on a condition, where it's arranged like this, where it's basically like all of them are going to be one side like this, and then there's basically some trigger point like this, where it turns into the other set of items after that. Okay, so we'll just in general call this condition based. Okay, so let's say you have some array B, which actually what false is over here, so false, and then it eventually turns into trues. And what we're going to be doing is searching for the very first true. So that's going to take an array called R, and this one is not going to take a target. We're not searching for some target. So you would still initialize in the same way here. You would set L equal to 0, and you get R. If you get N is equal to the length of the array, then R is going to be at the position of N minus 1. But what you want to do here is while L is less than R, the reason that needs to be less than R is because we actually need to force this to escape at some point. In normal binary search here, you basically are going to naturally escape because you either crisscross or you found a value. However, as we'll see here, we actually need to force it to escape, particularly when they are equal to each other, because when L and R are equal to each other, that is when they are going to land on the thing that we're actually looking for. And so we need to escape in that case. So you still get your middle index M is equal to, we'll just do the L plus R over 2 method. So in general, the above one is preferred, but this is usually fine. So then what you would do in this situation is you basically check your condition. So if the array at B at M, and more generally this might be some sort of function based off of the array, although for us it's quite literally an array of trues and falses. So for us it would be B at your middle index of M. If this evaluates to true, maybe we were in this scenario where we had L is here and M is here and R is over here. So we're searching in this space. So since M evaluates to true, we know that we don't want the stuff on the right. So we want to kind of move this over here.
Right equal to M.
Sure that this one is okay. You can't jump all the way to M minus 1 because you could have had this scenario. This would have had the same situation. And if you did jump R to be M minus 1, saying it to be over here, well then you basically started to be in the realms of the falses, and you don't want that. So in this case we set R equal to M so that we stayed in that realm of the trues. So in this case we would set R equal to M. Then basically it would be otherwise. So if this was a false, so if you had a situation like M is over here, well then you know you're in the realm of the bads. If M is bad, then you really don't care about all this stuff here. So you would want to set particularly L is equal to M plus 1. Okay, and in this function we're not just going to return true and a false, we would return either L or R. And it actually doesn't matter which one because this algorithm will particularly stop when L is equal to R. So it would stop in this scenario right here. And so again, that's why we need this particular condition of L is less than R, because when they are equal to each other, that's going to force this while loop to stop. So let's just call this, so binary search condition on our array of B, that is going to return us 4, which is 0, 1, 2, 3, 4. If we update it, so let's set this to be true, now it should be 3. Okay, let's set this to be true, it should be on 0. No, it returned 3. Well, the reason for that is because this is an invalid input for this. It's not just that it's a Boolean array, it's that particularly you have this arranged so that all the stuff on the left side are one type, all the stuff on the others are another type. Now let's just do one final example here, where we basically have false all the way across, and then we're looking for the final one there, which is 6, 0, 1, 2, 3, 4, 5, 6. That definitely seems to work. And again, I'm not going to write it, this would have the exact same time and space complexity. It's a very, very similar algorithm, just a slight tweak on the while loop condition and a way that we're adjusting them. Okay, so I hope this was helpful. Drop a like if it was, and have a great day, guys. Bye.
Alright. So I want to go search in third position. We're given a sorted array of distinct integers and a target value. Return the index if the target is found. If not, return the index where it should be if it were inserted in order. Okay, you must write an algorithm with log of n runtime complexity. Okay, it is easy. I can just return okay 7. So let me quickly go. So okay, there we go. Length of nums, L is 0, R is n minus 1. Then we go while less than L is less than equals to R. Okay, M is L plus what is R minus L, integer division 2. Right, division 2. Then we go if okay, if target if target less than, if target is less than number m. Okay, if it is less, so we update R equals m minus 1. If target is greater than number of m, we will update m plus 1, and else we go return m. Okay, right, yep. Okay, let's try this. Please try reloading the page. Okay, let's log in. Alright, let's see how it measures up. Okay, if it is not found. Okay, so if the target is not found, I want to return L. Yep. So yeah. Okay. Okay, great. Great. Okay, so we have the first bad version. You are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. Okay, since each version is developed based on previous versions, all the versions are bad. Okay, so I want to find is bad version. Okay. So input is n. Okay, if bad version API is defined for you. If bad version receives an int. Okay. So we will again start with, that is the condition based. Condition based binary search. Make sure to update r equals m and to check loop condition for L less than R, since at some point all L, R and M will have the same value and we specifically want that value. Okay, so we go L equals 0, store n equal ln of this one, while L is less than R. I can go middle and this will be, close it, this will be L plus R minus L integer division 2. So close it. Alright, so we'll go if let's say if bad, we want to find the first false, right? So if it is true, we keep on updating. Right, so we won't return anything. If bad version is n of m is a bad version, like, okay, if it is true, that means we are still in the left half. I want to update to m plus 1, else I want to update m, and when we come out of the loop we want to return uh, L, right? Yeah, we want to return, this will point to the first false. Okay, it has no len, first bad version. Okay, n equals 5, out bad equals 4. Oh, okay, okay, okay. So 5. So 3, 5, 5 and 4 is true. Alright. Okay, this is the length. Okay, so I already have the length. Let's go n minus 1. Object. Yeah. Okay. So add bad version of m. Okay. But expected 4 state output is 0. Right, okay, so first time 0 plus 5 by 2 is okay, maybe we start with n. Expected, okay. Okay, if I'm searching for 1, okay, 1 to n. Alright, so I'm searching for 1 to n. Okay. Bad is 4. Okay, so is bad version. Okay, so I want to reverse the conditions here. It is bad version. Okay. If this returns true, then we want to update the R. Okay. There we go. R equals M and L equals M plus 1. Okay, let's see now. Right. Okay, there we go. Well, that took okay, bad 1. So if I submit it, ooh, still so slow. What happened? Okay, binary search is bad version. L is less than R. Return L. M, right? Is bad version M. Which should I start with 0 and n minus 1? Does that make any difference? No. Okay, because it won't go to, yeah, least is 1. So, and I don't think it should. I think it will fail some test cases when it is 5. right? Yeah. Okay. So it has to be 1 to n. Okay, so min is 1 and max equals n. Alright. Still, okay, so is there a better way to do this? I have completed it, but let's say, is there a valid?
Hey guys, Greg here. Let's solve first bad version, LeetCode number 278. So we're approximately the latest actually ones to version number and find the first bad version showing it is bad for 4 because plus 1. So for each of these, if x is a bad version, aka if is bad version, you can see we have this first bad version. It's too slow. So these are all of our versions. So part up until the end. So that's when we n the probability, which is why now when numbers on this do, which is we'd have L middle value be 11 over 2. Have our middle value, and we would just call our function. We'd say, is this a bad?
Okay, if I make it does it make any difference? Well, it is much slower this time. How? Wow. Okay. 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 All right. Because the condition is 2 to the power 31.
Bad version? No, actually this version is just fine here. So we are looking for the first bad version. Well, if it's organized like this, a bunch of check marks, and then it's going to be a bunch of x's starting at. So we'd set L to be m plus 1.
Okay.
Is m. Remember that when we had a good version, I'll just call that GV there, good version, well that actually means that we should set L to be m plus 1. That makes sense because we don't want a good version, we want a bad version. So we're explicitly past m to the right. So our next iteration, although we don't know that we're ready to return it, it's a bad version. You would also don't here, for all we know, that is a good version. So we know we can't. And we would now
know this condition.
M is equal to when we have a good. These two are equal to each other. That is when we actually get the result. This is to be a big old log. Okay, so we set this to each other.
Right.
2 we have
right.
M. We wrote down M.
Right.
So we'll move as we can. This will keep running and each other. So do the same thing in a log solution. Okay, so just to be clear, the time complexity here is going to be big O of log n. And
okay, but my question is, valid perfect square. Okay, but my question is, what are these people doing here? Lambda open display underscore runtime.txt. Okay. Well, left is less than equals right. First bad equals and default to worst case. Okay. So, but first bad equals mid. Okay, return first bad. It's just the same version, right? I don't know. Maybe something. Okay. So I solved 2 questions today. These are search position. Well, I've actually implemented this one, Okay, so my solution. Let's go to and algorithms, to binary search. Oh, say binary search. Ah, my solution file. Okay. So I'll go with 2. I think it was insert position, right? Search insert position. Alright. So let's copy this. My deletion form. LeetCode. This is 35. Search insert position. Okay. Let's close this. And then we have, after search insert position, is this first bad version. Okay. Simple. First bad version. Okay. My solution for let's go to 78. 278. Okay. First bad version. Alright, I think that's enough for today.